Hello, everyone. Welcome to the H+C Webinar, the Electrification of Heat. My name is Dr. Andy Smallbone. I'm an Associate Professor at Durham, and I'm the Director of the Network Plus. This event's been organised through the EPSRC Network Plus for the decarbonisation of heating and cooling, and is part of an ongoing series which looks at the different challenges of decarbonising our heating and cooling sector and behaviours. So this month, we are delighted to welcome speakers who are leading policy and research around the topic of electrification of heat, and we're grateful to both presenters providing their time today. So the next speaker is Dr. Iain Staffell, who's a senior lecturer at Imperial College. He's from the Centre for Environmental Policy. Iain's research centres on decarbonising electricity systems, ranging from the economics of battery storage and the productivity of offshore wind farms to efficient ways of integrating renewables into electricity markets. We can hear you, so take it away.
Okay, well, thank you ever so much for the invitation to speak, and thank you also to Matt for the really interesting presentation about what has been going on in government. So I'm here with joint work with one of my researchers, Nathan Johnson, and Stefan Fenninger, who is from TU Delft. And it's a piece of work that's been funded by the NUPA project, which is Network Headroom, Engineering Upgrades and Public Acceptance. One of those where the academics had a bit too much time to come up with a complicated acronym, as with all funded research projects. And our aim here is to have developed a model that is capable of simulating demand for heating and cooling at multiple spatial scales and over very long time scales. So, for example, Matt has explained the results that they've got from these heat pumps that were tested in Scotland and the northeast and the southeast. But you might ask, how would they perform if they were put into the southwest or into Wales, where the climatic conditions are a bit different? Or they've been tested over the previous 3 years, but these have been 3 years with relatively mild winters. What could we expect in terms of the amount of demand that they are supplying and the efficiency of them if they were instead operating over the past 30 years? And those are both very difficult questions to answer. And so we set about trying to build a model that could help people get into grips with that kind of thing. So I'm not going to start with any motivation on why you ought to care for this, because hopefully if you're on this seminar, you care already. And also Matt set out very clearly the urgency of needing to change the heating technology mix that we have in the UK. So I want to focus on what are the many complicated drivers that demand has. So obviously demand for heating and cooling is subject to the weather. That's kind of obvious. It also depends on the infrastructure that you're in, so the characteristics of your building. It also depends very critically on the people inside those buildings. Two adjacent houses on a street can use a factor of 3 or 4 different in terms of natural gas consumption, with the old adage being that if you've got teenagers, then you can guarantee you're going to consume twice as much as you want to, because they'll always have the heating on at full. And then if you're thinking not just at the building scale, but at the national scale, population density plays a key part, because, say, the UK overall gas consumption is heavily skewed towards what the weather is like in the Midlands and London, because that's where the main population centres are. Then all of these things have their own subdrivers. So climate change is going to affect the weather quite dramatically. So it's not just going to get uniformly a degree warmer, it's going to increase the variability from day to day. And also this variation from day to day matters a lot more if we move to an electrified heating system of heat pumps, because the critical issues of balancing the power system hour by hour, second by second, whereas with natural gas, we have several days worth of storage and there's lots of flex in line pack in the transmission network. So building characteristics depends on what happens with building standards, with insulation rates, economic growth. Public attitudes, things like the shift towards working from home have changed quite a lot about how we use our buildings. And then there's the drivers of population growth and this continual shift towards urbanization that's changing the kind of geographical nature of demand in the country. So all of these factors together mean it's a very complicated system to try and model. And then we think about what's the ultimate wish list for a model that, let's say, we could simulate what the demand from these houses would be for heat in 2030, given climate change trajectories. It needs to be simple so that it's easy to use and it's possible to apply it to different situations. It needs to be global in coverage because I'm not just interested in the UK. These kind of issues are playing out around the world. It needs to be accurate because if you can't trust the numbers coming out, what's the point? And it needs to be customizable so you can play what-if scenarios. So by simple, you need to be able to apply it with high-level, widely available data. So I'd say the gold standard in building model are these sort of building energy simulation models, but they are very, very complicated because they go into the minute detail of the U values of each component of a building, very detailed measurements. So it can be an entire research project just to characterize a single building, and you can't then transfer that learning across to another building. It needs to be generalizable to all geographical contexts, so you can simulate one place or another. Statistical models are another important tool in this area. So people use machine learning to try and characterize what demand looks like in an area. The problem with machine learning is there's no extrapolation capability outside of the training data set. So if you've trained it on the north of England, it's only going to work on the north of England. It needs to be validated. And there you have a problem with standard degree day models because they are simple, they are generalizable, so they hit the first two of our requirements, but there's not been very much work done to characterize their accuracy against real world monitored data. And it needs to be customizable so that you can play games with it and see what would happen. So expectations, I would say in this case, are rather high. It's kind of like we want to be able to have our cake and eat it. And I'm thinking of cake because recently it was my son's birthday. So the last month of my life has been trawling online recipes to look at wonderful cakes we could make. And we really want to avoid with this model the fact that reality may not match expectations. So these are not actually my culinary creations, but they give you an indication of how things can not turn out quite as you want. So we need to avoid that. Right, I'll try and go through the methods that we have developed for this model that we call the Demand.ninja. It has a stupid name so that you have a chance of remembering it beyond the end of this talk. So the things that we want are building level energy demand, hour by hour basis for anywhere in the world, or national energy demand. And the thing we start with is gridded weather data coming from global weather systems models. And then you can supply some coefficients for how different weather variables affect your perceived temperature, and use those two things to calculate something that we call BATE and then smooth it. I mentioned at the start that academics love their acronyms. So what is BATE? It's like a feels like temperature for buildings. So if you look on your phone, you might see the weather today is 8 degrees outside, but some apps will tell you that it currently feels like 4 degrees because it's overcast or it's windy. And those things will change how you perceive the temperature. So that is focused on an individual person out in the elements. We're more interested in what an individual person would feel if they're inside a building that is not being heated or cooled. And then you can see in the chart over this side, for example, if it's a particularly sunny day, the points that are coloured yellow, then it will feel warmer than the outdoor temperature would suggest because you've got solar gains coming into your building. If it's particularly windy, the purple data points here show you that it will feel colder than it actually is because the UK is very good at building rather leaky houses that have regular air changes because of drafts coming through. So just to see what do those things do in practice. So the top chart you've got here, the pink line is actual temperature, UK-wide average, and then the black is our building adjusted internal temperature, the BATE. So if you look at, say, March and April, the two are reasonably in agreement with one another. But then compare that to November and December, that I've just highlighted here, you can see that the perceived temperature, the BATE, is a lot lower than the actual temperature. So actually the perceived temperature in November and December was similar to what you'd get in March and April, even though actual temperature was much higher. The reason for that is in the bottom panel. You can see that during November and December, we're getting almost no solar irradiance. The days are very short. The sun never barely pokes its head above the horizon. And that makes it feel a lot colder than it actually is. And we found that this particular modification is especially important in the high latitude countries such as the UK and really helps to correct errors that you get around autumn and early winter demand levels. You can also see here the impact of thermal smoothing. So there's a thermal lag effect in buildings because they have a thermal inertia. And so you can see in the pink, there are sort of spikes of high and low temperature on individual days, but they don't last long enough to completely perturb the temperature inside a building because it does have some insulation. So we've got our sort of modified temperature index. We do some corrections for hot weather because people's behavior is different when it's hot than when it's cold. For example, you're more likely to open your windows overnight when it's hot, so you're flushing air through the building. And then you can use that to calculate HDDs, so heating degree days or cooling degree days. And for that, you need temperature thresholds below which you want to heat or above which you want to cool. So really what we're doing is a variation on a heating a degree day model here. That set of steps can get you your building level heating or cooling degree days, which you could then translate into energy demand with some coefficients to explain how the heating and cooling systems react to changes in temperature. Give you an example of what I mean here. You can see the electricity demand measured over the course of a year from a single house in Texas. And I've picked Texas because they've actually got some cooling demand, so you get a more interesting chart here. So we need 5 coefficients to represent this demand profile. The first are those balance point temperatures that I mentioned. So you can see quite clearly there is a particular temperature below which this household starts to heat itself and a temperature above which it starts to cool. And then with a bit of machine learning, you can identify those points numerically, and then you can fit straight lines to the demand at either side. That then gives you the energy coefficients that you need. So there's this house consumes an additional half a kilowatt hour per day for every degree it gets colder, and it consumes an additional 0.6 kilowatt hours per day for every degree it gets hotter above that cooling threshold. And then there's a baseline demand. So this is looking at electricity demand, and your house uses that for appliances, lights, etc. Not all of it is due to thermal demand. So those 5 parameters and your building temperature index, you should be able to simulate demand. And just as a caveat, we look at gas and electricity demand in these slides, but you can model other measures such as actual raw heat output if that's what you choose to calibrate against. The final step then, if we want to get national energy demand rather than building level, is to do some diversification of these heating profiles and aggregation across the country. So by diversification, I mean run that whole process many, many times with different parameters selected across sort of a population to represent how people are different and what they want to do differently. And then aggregate across the whole country so that you're reflecting the fact that the weather can be different in Scotland and in Cornwall at the same time of year. To see how this works in practice, so here we've got raw temperature against natural gas demand across the whole of the UK. So you can see there's a very clear relationship, but it is quite scattered. If you instead look at that with relation to our temperature index instead of raw temperature, a lot of that scatter is taken away and you've got this nice clear relationship instead. But when you do the fitting of the temperature set points, you see this is actually a very curved shape here, not a nice neat elbow joint as you tend to get in individual houses. Part of that is because the weather is different across the country, but part of it is that some people only heat the house to 15 degrees, some people heat it to 22 degrees. There's a huge variation in the population, so you can't represent it with a single temperature threshold. You need a wide range of thresholds, and you also need a wide range of all the other parameters that go into the model. So if we try using this process to model natural gas demand across the UK, we do so with an R-squared, so a coefficient of determination of 0.99. So it is a very, very accurate method. So you've got temperature up at the top, you've got the heating and cooling degree days in the middle here, no cooling degree days when you're looking at natural gas demand because we don't have gas-fired air conditioners, and then the actual time series of demand at the bottom here. And you can see events such as the Beast from the East back in 2018, when it was especially cold, registers as very high demand. If we look at electricity demand in the UK, similar picture, similar R-squared, but now you can see at the very upper end, when we have a heat wave, that one day of the year where it's hot in summer, you can see it registers as some cooling degree days, and you do see a spike in demand as well. We can apply this to other regions. So here is New York, for example, much hotter than London in the summer, much colder than the UK in the winters. So they have both heating and cooling degree days and big spikes in their electricity demand during the summers, because obviously all of cooling is delivered through electricity, whereas only a fraction of their heat is delivered from electricity. Final example, I'll look at Texas. Again, Texas is ruthlessly hot throughout the whole of summer. So you've got this very consistent high number of cooling degree days. And then you have specific cold storms come through in the winter, which cause big spikes in demand. So what we've seen is that modeling regional or national scale electricity demand or gas demand can be done very accurately with this method. Then very quickly to finish, think about a couple of example case studies that you can do with this. What kind of questions could be answered with a tool like this? Now, the big issue over the last couple of years has been how can we save natural gas? Because prices have shot through the roof. Putin blew up Nord Stream. Don't libel me on that if it wasn't actually him. But we've had a gas crisis, and Europe as a whole has saved about 15% of its natural gas demand compared to previous winters. So there's a thought of what actions can individuals take to reduce their gas consumption? So this is the profile of natural gas consumption from a typical UK house, sort of average level of consumption. And we wanted to model, well, how much would they save if they turn their thermostat down by a degree? So calibrate the model to match this house, and then shift its set point for heating down by a degree. And then you get from the blue line to the green line. It saves about 6 kilowatt hours per day during the heating season. Then repeat that across a model data set where there's 2,000 or so houses that have had their consumption metered. And we find your average house is saving 9.5% of their natural gas consumption. And these range from about 8 to 11% across the population, because some houses are heated for longer in the year, some are heated to a higher temperature or a lower. Span that out across the whole of Europe, and then you can see, for example, the savings per person are around about 1,000 kilowatt hours, or 1,200 in the UK. So that's looking at about 100 euros. Not the right currency for us, but it's the currency that the rest of the continent's pretty much using. So that's the one we went for. Savings across the whole of the continent are the equivalent of nearly 70 million tons of CO2, over 1,000 billion cubic feet of natural gas. And in economic terms, you're looking at 30 billion 30 billion euros. And the savings in different countries scale based on how long their heating season is. So the UK saves a lot because we're relatively cold. And what's the penetration of natural gas in heating? So again, the UK, Netherlands, Belgium are the big ones here. Just wanted to have something on the global scale, because it's not all about Europe. So what I want to advertise here is that we now have this accessible data set with global coverage, 40 years of duration. So you can now start to model things like what's maximum temperature across different parts of the world, and how is the burden of cooling needs shifting because the planet is warming up. So you saw how in Texas and New York, we were modeling how many cooling degree days they're having over time. Here you can see how these have changed since 1980 to the present day. And it's sort of the Central African region, places like Cameroon or Central African Republic are seeing 150 more cooling degree days per year, per year, each decade as time is going on. So some of the hottest parts of the world are really getting even hotter. But when you look in relative terms, it's Eastern Europe, it's Southeastern UK that are seeing the fastest growth in the burden of cooling. So I just zoom in on Munich here. Look at the 1980s. They averaged only 20 cooling degree days per year, and it's now more like 60. So it has increased by sort of 40% per decade consistently over the last 4 decades. So while we might be very focused on heating in the UK, cooling is going to become a big issue in the future. Very last 2 slides is to show you the reason we called this Demand.ninja is because we have an existing tool called the Renewables Ninja. And when Andrew introduced me, he said, my background has been in modeling resources from wind and solar farms. So that's a website that lets you do this. And then we've now got the Demand.ninja website. So this is just a demo of what you can do on it. If we zoom into Durham, we could say, look at Durham Castle and then query what would be the demand for heating over the course of the year. If it was heated to an internal, if its heating system came on at 14 degrees, then this is the profile of demand they would have. You can then play around with the parameters. This is how it would change if you went to a heating threshold of 16. So you could play around with different places, with different properties for the building, scale it up according to the actual demand, because these are all just normalized numbers, because I don't know how much heating Durham Castle needs. But you go to the website there, join the beta test, and you can start to play around with this yourself. So I hope that was interesting. But to conclude, so there's a free platform where you can access weather data, degree day data, or run your own simulations of heating and cooling. We've demonstrated some of the things that you can do with this Demand.ninja model in the talk today, but I think there are many, many more interesting and more useful questions that this could be used for. And I don't have the time nor the brain power to think of these, so I'm hoping I can turn this over to you and you can use this as part of your research to start answering these things. Very happy to take questions and comments, and happy to email you the paper that this is all based on if you're interested. So thank you very much.
Great, thank you, Ian. Thank you very much. All very, very interesting. I'll have to have a look at that in a bit more detail. I'd heard it, the .ninja thing, and I was having a look at